Dear students, now we go to the Module 9 of Unit 3, which is related to the bandwidth efficient PCM techniques. That means now we are having compressed quantization. So now we try to reduce the number of quantization levels by reducing the dynamic range of the signal. Earlier we have seen if we have a larger dynamic range, means if the span of this signal in amplitude is larger, we need large number of quantization levels to reduce the quantization error. So now we try to reduce the dynamic range of the signal, and we have less number of quantization levels while we are converting analog signal into digital signal, and that's how we have a bandwidth efficient PCM technique. So there are so many techniques, mainly 5 techniques we are using to achieve this compressed quantization. First one we call a differential PCM, abbreviated as DPCM, then adaptive differential PCM, abbreviated as ADPCM, delta modulation, DM, adaptive delta modulation, ADM, or it is also called continuous variable slope delta modulation, CVSDM, continuous variable slope delta modulation, CVSDM. And last one is sigma delta modulation, SDM, which is very much popular in the high data rate system. Let me go to all these 5 techniques one by one, and we see the transmitter and receiver block only and their operation. First, let me see the principle of the DPCM, differential pulse code modulation quantization. So here in all these techniques, we are keeping the sampling rate higher than the required Nyquist rate. So now if we keep the sampling rate higher, then we are getting the samples which are very near in time. Now the practical signals like voice, video, the adjacent samples differs very little in the amplitude because they are highly correlated, so that they contain the redundant information. So now instead of quantizing the absolute amplitude, we quantize the difference between the successive amplitude, so we can have the lesser dynamic range of the signal. So all this you can say the bandwidth efficient quantization scheme are using this principle, and DPCM uses the differential principle here. So in DPCM, quantize the difference between the present sample of the signal and its predicted value by a system. That's called the predictor. So here we find a difference between the present value of the sample and a predicted value by a system called the predictor. The predictor is one kind of filter here. So that predictor is the part of this DPCM quantizer here, and that predicts the present value, and whatever be the correct present value, we subtract from this the predicted value subtracted from the present value, and the error, or you can say difference, is quantized. So the difference will be very small if the predicted value is very near to the actual value. So all things depends on the correct prediction. So the predictor is very crucial circuit in this DPCM. So here how to predict the value. So the predictor circuit predict the value depends on the past n sample values. So it stores the past n sample values, and from that it will predict by having the linear combination of this past n sample value, and the prediction must be as close as to the present sample value. So here we have a block of this DPCM. We will explain the detail of the predictor circuit also. So in you can say simple block diagram, we are using linear predictor. As I mentioned, it uses the linear combination of the past value of the sample, and that is achieved by using the transversal or tapped delay line filter, and that filter is called transversal or tapped delay line filter. It is basically FIR filter. It is one kind of digital filter which is called the FIR, finite impulse response filter. Its tap length is finite, so it is called the finite impulse response filter. Now let me go to the block diagram of this DPCM transmitter. We have analog signal as usual. We need the anti-aliasing low pass filter and sample and hold circuit to achieve a discrete time version, which is GN. Okay. Now in ordinary case, if it is PCM, we have passed this GN to the quantizer, and then we binary encode it. But now instead of having a simple quantizer, we have this block, which is now DPCM quantizer, which is the DPCM quantizer. So now we have this input and GN and one more input we are generating, which is called GPN, which is the predicted value of this GP, and it is predicted by the predictor circuit, and that predictor circuit is actually linear predictor of nth order, right? And here we are using one difference or subtractor circuit which generates an error signal Dn or difference signal Dn by having Gn minus Gpn, right? And that difference signal, if this predicted value is very near to the actual value of the present sample, is very small, right? Here the difference is very small. So the dynamic range of this signal is very small. So here we need the less number of quantization levels to quantize this signal compared to this signal. In that way, we require less number of bits per sample, and in this way we can reduce the bandwidth required, right? Now the important part is this, okay? Now let me go to first the detail of this predictor. So as I mentioned, it is tapped delay line. So it has Gn as an input. So this predictor has a Gn as an input. Here we have indicated. We will see how to obtain this input to the predictor. We have Gn as the input to the predictor. It has n number of delay elements, right? So z raised to minus 1, z raised to minus 1. So these are all delay elements. So each element delay by one sample. So output of this block is Gn minus 1, and n such blocks are there. So final output is Gn minus capital N. Now output of all these blocks are multiplied by prediction coefficient a1, a2, an minus 1, an, and they are summed by this summer. So it is generating here Gp of n, right, which is the predicted signal Gn. It is predicted signal Gn. So this is the structure of the linear predictor, which is nothing but an FIR filter, sometimes called transversal or tapped delay line filter. Now question is how to obtain this signal here. Now we can use directly this Gn, but this is unquantized signal. So we have to use the quantized version of Gn here, which is Gqn. So that we can derive by taking the feedback. So here this is the block. We have this Dn, and here we have a quantizer. So output of this quantizer is Dqn. Now what Dqn consists? It is Dn plus Qn. What is Qn? Quantization error, because when we pass any signal to the quantization, it's subjected to the random quantization error. So this Dn, when passed through this, generates Dqn, which is equal to Dn plus Qn. Now it is passed through this adder circuit. Now this adder circuit has here this Dqn, which is actually Dn plus Qn is input, and another input we are taking from this feedback path, which is the output of the predictor itself, Gpn. So that is equal to Gpn plus Dn plus Qn. Now if you see here this Dn itself is Gn minus Gpn. So if you substitute here, this will be here Gn plus Qn. The signal here will be Gn plus Qn, and that will be Gqn, quantized version of Gn. But the quantization error is small, so we can say it is approximately Gn. So we are using this signal as an input, not the actual Gn, because this is unquantized version. So we are using its quantized version, because all these blocks of this quantizer must use the quantized version of the signal. So we are using here this quantized version by having this feedback mechanism, and in that way the output of the predictor is Gpn, which is used here at the input to this subtractor, as well as we have taken it as feedback for the input to this adder, right? So this is basically a block diagram of DPCM, and finally once we have the quantized signal Dqn, we can feed it to the binary encoder, and then we can have a line coding to generate the waveform. So that generates the DPCM data, right? So this slide explain all these things that I have explained, right? How Gqn is equal to Gn. Also for nth order linear predictor, we have seen the equation we can describe like this: Gpn, which is output of this predictor, is equal to sigma, right, k running from 1 to capital N, ak g of n minus k. So you can see this Gpn is equal to a1 into gn minus 1 plus a2 into gn minus 2 plus a3 into gn minus 3 dash dash dash, plus you can say an minus 1 into g of n minus capital N minus 1 plus a capital N into gn minus capital N. So this is represented by simple summation like this, right? Where all these AK are constant coefficient of the predictor. They are fixed coefficient, constant coefficient. So here these coefficients are very crucial because that decides how much your predictor gives the value GPN close to GN. If this value is close to GN, it is almost a zero, you can say, difference, and the number of levels required are very small. So this will improve the bandwidth. So predictor is very crucial circuit. Now what will be receiver? If we do this, what will be receiver? Now in all this kind of PCM system where we are having the bandwidth compression, we have some feedback path at the transmitter, and that feedback path is actually the design of the receiver, because at the receiver I have the last block of the transmitter is encoder, so I can easily pass it to the decoder to get the signal DQN. So actually my input at the receiver is DQN signal. So I have a decoder circuit which is opposite to encoder, and I can get easily the signal DQN completely if the channel is noise free, right? So my received signal is always DQN. Now if you go to the transmitter block, we can derive the receiver block. If you have this signal available, I need to obtain this signal GN. So what I need DQN plus this signal GPN. So our GPN is generated by predictor. So I need the same predictor circuit which is at the transmitter if it is at the receiver, and the output of the predictor is summed with the available input at the receiver which is DQN, I can get the signal GN. So the receiver block is very simple. I have the adder circuit. One of the input is DQN, another is GPN which is from the predictor. Predictor has input GN which is actually approximated version GQN, because all blocks here have the quantization error, and this GQN is always output of this adder because DQN plus GPN gives me the GQN. So we can take it as a feedback, and this gives me the generation of GQN. Now the GQN is always having some quantization error. I cannot remove this quantization error anyway. There is no reverse of the quantization. So I will pass it to the interpolator and low pass filter to generate the signal back, analog signal back, that is reconstructed signal GT, which is G cap T. So in this way, by using the same predictor at the transmitter and receiver, we will be able to recover the signal back. So this is DPCM transmitter and DPCM receiver. Now what are the advantages? As I mentioned, to achieve the same SQNR, the DPCM needs less number of quantization level. That means less number of bits per sample compared to PCM. Say for voice signal, 3 to 4 bits per sample in DPCM give the same SQNR performance as 8 bits per sample in PQS. So here the bandwidth required is almost half compared to PCM. Say if I want to transmit television signal through telephone lines, we have discussed the TDM technique where it is also possible to transmit the television signals which are requiring very high data rate, right? So in that case, if I use PCM, the bandwidth required will be too much. So instead of PCM, I can use the DPCM. And in some countries, this is practically installed where using the telephone lines, we are getting the television signals, and in that the DPCM is used. So DPCM offers a saving of almost 18 Mbps over PCM if you use it for the television signal, right? Now this DPCM has one very important thing is the predictor. It's all, you can say, the bandwidth compression and all its performance depends on this predictor, how much correct this predictor is. If the predictor is not correct, the performance is not good, right? So there is one solution. The solution is adaptive DPCM or adaptive differential pulse code modulation. So in this scheme, now the coefficients, the prediction coefficients are not fixed, but they are updated continuously by using adaptive algorithm. So we have one block here which consists of the adaptive algorithm, and here is logic for this adaptive prediction. So this will continuously change this coefficient AK of this predictor so that this predicted signal GPN is very close to GN, and this difference is almost 0, and we have very good you can say compression here. So all other blocks are same. The additional thing is this logic for adaptive prediction which consists of the adaptive algorithm, and here the inputs are this GQN and DQN depends on this. We have the adaptive algorithm like LMS. list mean square. It is actually very complicated algorithm to describe here and beyond the scope of discussion of this subject, but that algorithm is a part of statistical signal processing or adaptive signal processing. So it is very sophisticated algorithm, right? Adaptive algorithm, and it is called LMS algorithm, and there are so many other variants of the LMS are available like NLMS, RLS, but they are beyond the scope of discussion here. So this kind of sophisticated algorithm can be used to make this coefficient adaptive, and hence the prediction accuracy will be improved, right? Now if we have this at the transmitter, remember receiver use the same adaptive algorithm strategy. So whatever we are using in the feedback path in the transmitter is actually my receiver. Now further simplification possible at the cost of some accuracy is the delta modulation, which is the simplest kind of the, you can say, quantizer. It is the simplest kind of quantizer. It's a simplified version of this DPCM. So here again at the transmitter we sample the signal at the higher rate than the Nyquist rate. So we have this sample signal Gn available. Now the system is same as the DPCM, but now the quantizer here is simple 1-bit quantizer. It is simple 1-bit quantizer. So here it is only 1 bit per sample. Each sample is assigned only 1 bit. So greatest reduction in the bandwidth is achieved, right, to this different signal. Also the predictor is only first order predictor. So it is single delay. It depends only on the one past value, right? It predicts the, you can say, GPN depends only on the one past stored value, right? So this is a very simple predictor, only first order, which has single delay element. Now if I combine this adder and this delay element, actually this will become an accumulator. You can see here, and this is an adder, and this will store one past value and it is added with the present value. So we can say this system is an accumulator. And accumulator output is a feedback signal which is given to this subtractor circuit to generate this difference of error signal here. And then here only we are using 1-bit quantizer. So how this 1-bit quantizer works? It is simple comparator or hard limiter, right? So how it works? So if, let me say, the step size of this quantizer is delta. Let me say the step size of this quantizer is delta. So if my this signal Dn, which is actually Gn minus Gqn, if this signal is greater than 0, that means Gn is greater than Gqn minus 1. Why this is Gqn minus 1? Because this is Gqn, as we have discussed earlier, this is Gqn, so this is Gqn minus 1. So if this signal is greater than this signal, this is positive. So if this is the case, the output of this quantizer is simply delta, say some value, step size. The step size is fixed here, it is delta. But if this signal is negative, means Gn is less than this quantizer or comparator generates minus delta, right? So either it is 1 or 0, 1 or 0, means it will just compare present value is greater than predicted value or present value is less than predicted value. In that way, we have only 1 bit per sample. So greatest reduction in the bandwidth can be achieved. So this circuit offers this simplicity, right, and great bandwidth reduction. But there are certain issues with this delta modulation. We will see here in the waveform. Let I have this analog signal. I have taken this as my GT, right, and let me take this GQn minus 1. So how this GQn minus 1 is derived? If I have the particular shape of the GT, right? Now I have the particular shape of GT. Let I assume some sampling instant, because I am working with the sampled version of GT, which is Gn. So let I say this indicate the, say, some sampling instants, right? Now initially there is always some startup interval. Let me assume that initially this is the available level at Gqn minus 1. Now if I start with this, my Gn is this, but Gqn is this. Gqn minus 1 is this. So what is here? This Dn is Gn minus Gqn minus 1. So right now my Gn is less than this. So the output is what? The output is minus delta. The output is minus delta, and this minus delta is available here as the input, right? So this minus delta is subtracted from the accumulated value. So the result is like this. Whatever be the accumulated, previous accumulated value is this, from this minus delta is subtracted. So one step size is down. Let I say this is my step size delta, which is fixed. Now the signal remains at this level during this sampling interval. Now again, when this is the next sampling instant, again my accumulated signal GQ and minus 1 is still greater than the actual signal Gn. So again the output of this quantizer is minus delta, which is subtracted from the accumulated signal to generate GQ and minus 1 at the next sampling instant, and due to this step size it becomes now negative. Now this is less than this, so now next interval it will be positive. Again the signal is remaining constant here, DC. So this keep on fluctuating like this. Now the signal start increasing. So my GQN is following it by either adding delta or subtracting delta, right? Here it is increasing, so this delta is added, right? Again it is constant here, so depends on whether it is greater or less. Again I have some pulses like this. Now at this instant the variation is too fast, the signal is changing too fast. So here my signal is greater than the accumulated value, so some delta is added, but it will not catch this. Again some delta is added because still value is higher, it will not catch this, and like this. But again when the signal becomes say of constant or having small variation, again it will catch up, and if it will become constant it will keep on fluctuating like this. So what I want, the prediction should be very much near to this analog signal, but here there are two problems. One is when signal is changing too fast, and second is when the signal is changing too slow, or the signal is having DC component almost constant. In that case this GQ n minus 1 is fluctuating between 1 and 0, 1 and 0. So unnecessary variation is generated while the signal is not varying, but the quantized signal is varying. So this will give unnecessary variation. So that is called granular noise. So it has one problem when this signal is constant, the analog signal is having DC component. Also, if analog signal is having high frequency component, very high frequency component, this delta size, if it is small, this will not able to catch up, and it has a problem of the slope overload. That is called the slope overload. It should match this but not able to match this. Anyway, but simplicity is always there, right? So there are two problems, right, that will be slightly, you can say, degrade the performance on accuracy point of view, right? Granular noise and slope overload. One is with the zero frequency problem, another is at the highest frequency is the problem. Now this step, or you can say staircase kind of signal we have shown is GQ and minus 1. And what is then DN? DN is GQ and minus 1, GN minus GQ and minus 1. So ultimately this DN is quantized to DQN, and which is either delta or minus delta. So from this I can also sketch the DQN. Say I will take this interval, right? Here it is going to minus delta, so during this interval it is minus delta, then here it is going to plus delta, so this will remain plus delta, here again minus delta, so minus delta, plus delta, like this. So depends whether it is increased or decreased, this DQN is plus delta or minus delta. So this is the actual signal that we have generated. So this is my 1, this is my 0, this is my 1, 0, then 1, 1, 1, 1, then 0, 1, like that. So this is my delta modulated signal, okay, but it has the granular noise here and some slope overload here. These two are the problems in the delta modulation. Anyway, if we have transmitter, what can be receiver? So receiver is again simple. This is in a feedback path, so here feedback path consists accumulator. So at the receiver I have DQN available as the input, so I need one adder, I need one delay element, actually I need this accumulator, right? And whatever be the output of this accumulator, I need to feed it to the adder circuit, I get my GQN back. So my receiver is very simple, right? Like this, same accumulator which is in a feedback path at the transmitter, now at the receiver, okay? And GQN is a quantized original signal, right, which is in a discrete time, so I can pass it through the low pass reconstruction filter and I get the analog signal back, right? So this accumulator is also sometimes called discrete time integrator. If you recall the signal system, the accumulator is also here discrete time integrator, right? But this delta modulation we have seen, because of the fixed size delta, have two problems: slope overload and granular noise, sometimes also for hunting because of the fixed delta. So what can be solution? Now to avoid the slope overload, we need the larger delta. But to avoid the granular noise, we need a very small delta. If the delta is very small, this granular noise can be easily avoided. If the delta is larger, this slope overload noise can be easily avoided, right? And in the middle, when the signal is not changing too slow or too fast, we need the moderate delta. So what is the solution? What can be the optimum value of delta? So there is an optimum value of delta in terms of the signal bandwidth, signal power and sampling frequency. We are not going to derive this optimum value of delta, but that delta we need an, you can say, an optimum value. Anyway, this delta modulator has this disadvantage and subjected to the advantage of simplicity and less cost. Now to overcome this problem, we can again use the solution like we have used in DPCM, that is the adaptive delta modulation here. So we add one adaptive algorithm to adjust the delta now, right? So depends on this DQN, we will adjust this delta. So delta can be now made too small, moderate or too large, depends on the requirement. So here we have the complex adaptive algorithm which decides the step size, which is not fixed now, dynamic, right? Otherwise structure remains same. But I use this at the transmitter, I need at the receiver. So at the receiver, again my DQN is the input. I need the same adaptive algorithm here which predicts this, which step size is used, and it will be fed to one multiplier circuit which multiplies this incoming signal with this predicted, or you can say the step size value. And now here I have one signal available, DQN here, right? So I can feed it to the accumulator and I can get back this GQN, right? The adaptive algorithm, as I mentioned, is here using some complex algorithm like SOM algorithm and space shuttle algorithm, which are again beyond the scope of discussion here, right? So this is adaptive delta modulation. Now the adaptive delta modulation has one more problem. Slope overload is there, granular noise is there. We can avoid it by using adaptive delta modulation, but in that case we need the adaptive algorithm, which is slightly complicated. So these are the problems with the delta modulation. Still there is one more problem in delta modulation. If you see its transmitter and receiver, then at the receiver we have the accumulator circuit on the input side. Now this accumulator circuit keep on adding the incoming values. So if signal is there, okay, but if there is also noise with the signal, here in analysis we have assumed all the channels are ideal here and there is no noise present with the signal, but in practice it is present. So now if there is any noise is also here, then this also get accumulated. It keeps on add, keeps on adding it. So that will create a problem in the receiver. So we must not need such kind of accumulator or discrete time integrator at this input side of the receiver. We must have to remove it from the receiver. If we have this block at the transmitter, there is no problem. So how we can avoid this block? So we can avoid this block by considering, say I have a delta modulation transmitter which generates DQN and it is connected in series with the receiver, so I can get back my signal GQN back here. Now if I take these two in cascade, the transmitter and receiver in cascade, so if I move this accumulator from the receiver to the transmitter, so I want to move here, I want to move it here. So what will be left out? Let me see in this figure. So I have redrawn here this delta modulation transmitter in a simple way. So I have this 1-bit quantizer and accumulator in feedback path, and in receiver I have accumulator at the input and then low pass filter. I will remove this accumulator from this receiver to this, right? So now the receiver is left out only with the low pass filter, very simple. But this accumulator is moved here. Now this is a linear system, so whether I place this accumulator here or I place at the beginning, right, ahead of this block or after this block, let I place it here. If I take this block here or this block here, it will not affect the performance because this is a linear system. So let I take here. Now see here, this Gn is multiplied by the transfer function of this accumulator, and whatever be the signal coming here is also multiplied by this accumulator which is in a feedback path and then generates the Dn. So there are two accumulators. Can we do something? to replace it by single accumulator? Yes. If I move this accumulator inside and I take this dqn directly here and gn and first generate the difference signal gn minus dqn and then feed it to the accumulator. It is accumulator transfer function multiplied by this difference signal dn, which is same here. It is accumulator into gn minus accumulator into this, right? So if I take this accumulator common here, then there is no problem. I need only this difference signal and then I multiply it by accumulator. So in this way, I have also replaced these two accumulators by only one accumulator. So I have not only reduced the hardware, but I have also reduced that problem. This accumulator accumulates the noise at the receiver. My receiver is very simple, which is low pass filter. So such modification in delta modulation is called sigma delta modulator. It is called sigma delta modulator. So this is my SDM, sigma delta modulation transmitter, and SDM receiver is very simple, low pass filter, right? So it is simple. It will remove that problem of the noise accumulation. Also here, the granular noise and slope overload will also be taken care. We are not going to analyze, but that will also be taken care here. So it avoids most of the problem of the delta modulation, and also it is very simple. It gives the greatest reduction in the bandwidth. So practically this SDM is very much useful in the high data rate system. So all things are explained in this slide, right? And as the SDM simplifies the receiver design and improves the noise performance, also it allows the quantization of DC signal and reduce granular noise. Also, as signal is integrated before the quantization, the slope overloading becomes less likely. So all the problems are solved by this SDM, and it is practically used. So this is the sigma delta modulation, and that will end our module 9. Now next time we go to the module 10, where now we will see the digital carrier communication, right? Still this module we have seen only the digital baseband communication. We have just converted analog into digital data and transmitted it without multiplying it with any sinusoidal carrier or modulating it with the sinusoidal carrier. So if I have the wireless communication, I have to do the carrier modulation, and that we will see in a next module.